Depeugh, and I'm here speaking with Jeff Nath on, we're going to talk on Hello? Okay, sorry about that. Quick question, is there anyone here who has not been in an ARP talk yet? Because I may just kind of blow through some of the beginning stuff since it's probably been talked to death already. Anybody at all? Okay. Go kind of fast then. Basically what we're going to talk about is a little bit about Layer 2. We're going to go over ARP and to a lesser degree RARP. We're going to talk about different ARP behaviors by OS. We're going to also detail a new router attack, and we may or may not go over the ARP poisoning thing because I think that's probably been done to death already. Basically, Layer 2 is part of the OSI model. It's the part we're talking about is the data link part. Basically, all network communications roughly follow some or all of the OSI model. The key thing to get out of this slide is that the purpose of the layers, lower layers provide services to upper layers. Layer 2 is responsible for addressing transmission, framing, and error control, and it provides transport services and translation services for upper layer protocols like IP. In an Ethernet IP environment is where you'll primarily find the ARP protocol, although it does work with token ring FIDI. Ultranet, I think, is another one too. Basically what it does is, it stands for Address Resolution Protocol, in case you didn't know that, and is Hello? All right. I feel like a rock star now. Okay. Basically what it does is it provides translation services translating MAC addresses to IP addresses, and the reverse is done using RARP. There's two types of packets, replies and requests, which you probably know. Requests typically are sent to the broadcast. Some other things to kind of note about ARP is the concept of gratuitous ARP, where when a machine, typically on boot, it will send out an ARP packet saying, who has my IP? If no one answers, then it knows that there are no IP conflicts in the network. Also important is the idea of ARP cache. Basically what an ARP cache does is it takes the information that ARP gives it and stores it so it can be referred to later. This helps cut down on network traffic and congestion. And Jeff's going to talk about the ARP packet format.
Hello there. How does this work? Okay. Bear with me, I'm not very good at this pointer thing here. We're pointing over here at the first 2-byte field in an ARP packet. It's a word-aligned field. That's the hard type. ARP can be used across a number of both link layer and network layer implementations. So this 2-byte field exists to basically say what's the hardware type. Generally for Ethernet, that's 1. The next field here, the other 2-byte word-aligned field here, the prot size is the, oh, you know what? We've got to duplicate. That's supposed to be, oh no, prototype, okay. Okay, the prototype field designates the hardware protocol type, and it's duplicated from IP in ARP packets. It's 0x0800, which is the same in an Ethernet frame, the 2-byte ether type field. The next 1-byte field here, the hard size is the number of bytes in the hardware address. The next 1-byte field, also 1-byte field, number of bytes in the protocol address. In our case, we're talking about Ethernet and IP, so for the hard size, that's 6 bytes, and for the prot size, it's 4 bytes. The opcode is sort of the magic here. This is what differentiates between ARP request, ARP replies, RARP request, RARP replies, and so on and so forth. For For ARP requests, it's 1, and for ARP replies, it's 2. And, 3 and 4 for raw ARP and whatnot. We're not going to really get too much into that. So these next 4 fields are, fairly self-explanatory. For the purposes of our talk, Ethernet and IP, the sender hardware address is a 6-byte field for your MAC address, the sender IP a 4-byte field, and the same for the hardware address and the IP address. So there's a couple interesting things here. This gets tacked on to a 14-byte Ethernet header. If I'm repeating stuff, forgive me. And some of this information is repeated. For example, am I putting it the right thing here? No, I'm not. The hardware addresses. The hardware addresses both appear in your Ethernet frame as well. We'll get into that in a little while, but it's important to note that specifically in an Ethernet implementation, you've got some duplication of information. I guess, yeah.
So what are some problems with ARP? These probably are repeats also, but I'm going to run through them quickly anyway. No authentication method. Means I have no way of knowing if the reply or request that I receive is actually from a legitimate machine or not. This kind of ties into the next issue, is that both replies and requests are used to update ARP caches on machines. So if I make an ARP reply, the machine will cache the information I use in the reply in its own cache. I think this was originally done to kind of help as far as network congestion-wise. The thought being, well, if you make a reply or request, either one, you want information, and you're giving me the correct information to begin with, so I'll go ahead and take that so I don't have to ask you later on down the road. Another issue, replies which do not correspond to requests are allowed most of the time by most operating systems. The one thing about ARP is it's very OS dependent on how it behaves, so none of these are actually true probably for every single system, even though the RFC says that this is how it should function. Another issue is new information always supersedes old, and there's no way to, what in my opinion would be nice is if sort of like you do in the router world, where you have sort of a hold down timer or something when a major change occurs. This doesn't do that. This says I may have had this information updated, many times over days, months, whatever, but I got a new piece, so I've got to update now. Another issue is it's not clear according to the RFC which fields in the Ethernet packet are used to supply MAC and IP information to the cache. This can run into you can run into some issues with this, and we're going to talk about that a little bit later on. Another one of the issues is static entries are not always static. Doesn't make a lot of sense to me why they would not be, but I've run into a lot of instances where they are not. And Jeff's going to talk about the ARP behavior by operating system.
So Kevin said that hosts implement ARP differently. It would assume that one would assume that because ARP is supposed to be hardware type and protocol type independent, that the valid information would be in the ARP packet itself for the hardware address and whatnot, specifically the hardware addresses. But as we see from these slides right here, that's not necessarily true. It looks like Solaris and FreeBSD, 4.2 and 3.5, they take their information from the Ethernet header, and that's kind of broken because Ethernet is just one implementation of ARP. So we're going to get into that in a minute. But basically what you got here is a fairly simple table, and why is this relevant? Well, let's think about this. To attack systems using ARP, it's sort of important to know how they behave with ARP. The RFC says that when we get an ARP packet, we look at whether or not something's in our cache, we look at the information, whether it be from the Ethernet header or the ARP packet itself. And whether or not we have an entry, we might cache it if we don't have an entry for it, or if we already do, we simply update. But once you can understand how a host actually uses ARP packet information, you can sort of decide, well, what kind of evil things can I do to a host? Some hosts will filter on different types of ARP packets. You send a host an ARP packet, and you have valid information in the Ethernet header, but malicious information in the ARP packet. Well, if you figure out that it filters on that ARP packet information, and it generates some sort of little message when you try to do some sort of evil ARP thing, but the event that is actually generated only pays attention to the Ethernet header, or I may have messed those up, but if your two implementations don't match, you can simply bypass filters. So in trying to figure out how different hosts behave, we tried to figure out how these hosts parse ARP packets so that we could target certain attacks at them. I guess let's take a look at the next slide here. All right, this is what I was hoping. How do we do this? We use Nemesis. Made a couple modifications to Nemesis so that we could, well, first figure out how different hosts behave, but sort of this first one up here, added Solaris-style ARP option. What does that mean? Well, when you send an ARP packet over Ethernet, you've got a packet that basically has, your Ethernet header at the beginning, and then a 2-byte Ether frame that says, I'm an ARP packet, and then this 28-byte field after that. Well, why does this even matter? You ask for an IP address by sending a broadcast, and you say, who has this IP address? Well, Solaris decided to duplicate the information in the Ethernet header. I don't know why, but it's supposed to be zeroed out, so it's kind of a really lame way of fingerprinting, but Nemesis can do it now. It's a little -S switch. I guess the proper thing to do would be to allow people to put either their choice of the Ethernet header and the destination address from the Ethernet header or the ARP packet independent. Doesn't do that right now. But the other important bit of information here, we can modify all the relevant ARP fields. You see, it's not exactly clear that these are completely independent of the Ethernet frame. They are, but that only really matters because you can use it on a lot of different link types. So what this means is that we allowed, you can change the source and destination in the ARP packet as well as the, Ethernet frame, and that's how you facilitate those tests to figure out, what a host cares about, what a device cares about, what it filters on, and whatnot. And it's this independence, that people generally fail to realize that they can really bite them in the end. If you don't understand what your host favors, well, you won't know how someone's going to attack you. And at the bottom here, you'll see this ARP-AN. That's really, how you show your ARP cache on a Unix system. -N numeric. Don't try to look up everything with DNS. And, ARP-AN Microsoft. They don't have any notion of that.
Tell them what the rev is and that it's up now.
Oh, 132 is up right now, but it's actually broken for this stuff that we're doing, but it'll be fixed very soon.
So pretty soon you'll be able to have the same kind of fun, I guess. So what? Who cares, right? Well, you've probably all seen and heard many times about ARP cache poisoning and sniffing and all that good stuff. So I'm not going to really go into that too much at the moment. What's maybe a little bit more interesting is what we noticed when you send some packets to some Cisco devices. Specifically, what we call the sonic boom. And if you know me, you know why it's the sonic boom. But essentially what that is the ability to smash the stack and essentially create a denial of service condition in Cisco routers. Run it on 11 code and 12. We've got 12.1 something running on this one. I haven't tried it obviously on every single Cisco device running iOS, but the ones I have tried, it all works. And we're going to give you a way so you can look and probably make a good guess as to whether it will work on your Cisco devices or not. And another thing to keep in mind too, that we are just talking about Cisco today, but I'm pretty sure that there are other networking devices out there that use a Cisco stack, and this would probably work against them too. So basically what we do is this. We send it an ARP request, and we say, I have your IP at my Mac. And it says, okay. And that's it. No more ARP. It does not update its cache. It does not respond to ARPs. The ARP cache on a Cisco is about 4 hours. So what you'll see is that over time, gradually hosts will just drop off the network as it loses their information in cache, assuming that they know where the router is in their own cache. For a lot of operating systems, this will happen in a matter of minutes. I think on Win2K, the ARP cache timeout is something like 2 minutes. So what you're going to see is just gradually things will fall off the network. And we're going to show you, give you a show right now how it works. Go plug in. far right. Yes. Okay, I'm going to sit down here. There we go. Basically, what I'm going to do to start with here is just to show ARP. I'm in enabled mode. You don't have to be to show ARP, but I'm in enabled mode anyway. And so here's what you see. You see that the first entry, 10.100.101, is a router interface. 10.10.82.54 is a router interface. You'll notice something kind of interesting, the age. They do not age out. These are permanent entries. And it's kind of interesting because if you look at the ARP cache of most devices, you will not see its own interfaces in there. It's partly because of this that we are able to overwrite this information. In my opinion, the Cisco, any device should not refer to its ARP cache to find out what its own IP is. I think that's generally a bad idea. And so we're going to show you why.
Real quick here, we're gonna do exactly what Kevin said. Send a little bit of information to our router here and see, give you guys an idea of how happy it is after that.
Okay, I just pinged the router to show that it does indeed work at the moment. Let's do that in a minute. Go ahead. So what you see is it generates a duplicate IP address message. It doesn't always do that. That's one thing to keep in mind, which is kind of strange. I haven't been able to figure out exactly why sometimes it does not. But this quite likely is your only notification that something bad is happening. You know, you might say, well, this is going to go off to the syslog server, so I will have some kind of knowledge. But if I can overwrite the ARP entry for the syslog server first, it's not going to go there. So now we do a show ARP, and we see that its new address is foo. And I'm going to go ahead and clean out my ARP cache, because the old one probably hadn't timed out yet. And now when I ping, nothing happens. And that's it. So now what you have is you've overwritten its ARP cache entry, and it stays like that permanently. Even though the ARP cache timeout is 4 hours, these persist and do not time out. So you can see why this might be a little bit of a problem. Any questions? Maybe?
Well, this is only the...
Sure. Oh, sorry about that. We've got it all scripted up to make it easy. But
Let me show you what's going on here.
yeah, he used Nemesis.
Basically, I send an ARP reply of the source of the router to the destination of the router out my network card, and the source hardware address in the Ethernet frame is foo, and the destination hardware address is the MAC address of the router's own interface. And to do the DOS, you have to use replies. We've tried every permutation on the planet. But as Kevin said, even upstairs testing this, we have many situations where it doesn't report, doesn't do anything, just silently accepts it.
Sure. That's what we're going to get to. You have remediated the problem. Go ahead. Yes, it does. Yes, it does. So it's not so bad that you have to reboot, but I don't know many engineers or administrators who know the MAC addresses of their interfaces on their Cisco's to begin with, so you might have a hard time figuring that out until the denial of service actually happens.
Yes. We have a patch.
No, because the remediation doesn't require a patch. And it's been my experience that if you can configure a fix, it's better than loading new code. At least in a Cisco, it generally is. And The configuration requires no downtime where a code reload would. Yeah. Yep. Any more? Okay. So, what I'm going to do, I'm going to clear the ARP cache. Let's clear ARP. And we're going to show it again. You see now that it's gone. It's back to the 0030. And it's all happy again. Now I should be able to ping it. Okay, so we fixed it. So, as the gentleman over there mentioned, if you put a static ARP entry in for its interface, it will work. It will not allow it to be overwritten. In my estimation, that's probably a good thing to do. And I know there's a guy next door giving a 25 security tips for routers talk. There maybe should be 26, I think. Another interesting thing that this allows you to do is some really cool sniffing stuff, because now I can be guaranteed that I am the gateway. I can be guaranteed that the gateway will not respond for 4 hours to ARP. So what I can do is I can now easily sniff both traffic in both directions. I don't have to use a flood of ARPs anymore, which is very noisy on a network. You tend to see it quickly unless you're on a flat network, and you got bigger problems than that probably. So it allows me to sniff in both directions. And basically what I can do is I can have my machine act like a proxy ARP and actually only respond when requested. So it looks like regular network behavior. You don't notice any difference. The same amount of ARPs are generated as normal traffic would generate. The only difference is the MAC addresses are different. And we are going to show that now.
Oh, aren't you?
So let me just make sure. Okay, so I'm back to normal here. Get rid of my cache. Okay. Okay, I'm going to go ahead and run it.
I'm going to run this script here, and then I'll walk you guys through what's going on. Let's go over here, fire up Snort real quick. Why don't you go ahead and ping this box over here, Kevin?
Okay, it's... Actually, let's just do this.
Wait, tell him not to it.
Stop, 20?
Yeah.
Okay, there we go. I'm through. He's running OpenBSD, so obviously he's not responding. And essentially what we've done is we've... now we sniff all traffic in both directions.
Sorry about that. Why don't you do that again? Just, okay. Now, there's nothing real magical about here. Obviously, I fired up Snort. It's a promiscuous mode sniffer, right? Okay. Let's take Snort out of promiscuous mode. Show that over again. Oh, lo and behold, we see all the traffic. We are not in promiscuous mode. And this is, no flooding of your switches, nothing.
So the only real indication that you're going to have that this is going on is if you know what the MAC address should be for your gateway. And most people do not. So, okay, we've... any questions about that stuff? No? Cool. Okay, I'm going to show you real quick how to actually add a static ARP entry, because I think that'd be a nice thing to do. Yeah, this presentation goes to 11, by the way. So basically what this command says is add an ARP entry with the IP address of 10.100.101, the MAC address of what the interface is, of the type ARPA. ARPA is the standard type for Ethernet. There are a few other types if you want to see what they are. There you go. Okay, I have added it. And you can see it show up right there. And now go ahead and try to run against it.
I'm going to use a simple DOS again.
Oh, one other thing to notice is that when you add a static one, it's no longer associated with an interface, which is a good test if you're actually just doing some show ARPs. Look for that interface, look in that interface column, and if you don't see anything, you'll know it's static. It might be nicer if there was like a switch or something that actually told you in this field, but it's kind of a good enough hint, I guess.
So here we go, we're going to DOS the router's interface again, or try to.
Okay, you'll notice this time no duplicate IP, and it persisted. It's still there. So it's a pretty easy fix when you get right down to it, but an important one, I think, nonetheless.
That only fixes the router, by the way. That doesn't necessarily solve the problem of all your end hosts, and I know that the last talk talked about which hosts' static ARP entries remain static and which they don't, and so we're going to get to that one in a little bit too.
Okay, so I'm going to jump back into the slide presentation here. Oh, and that's what we call the sonic boom, by the way. So what can you do to fix some of these problems besides a static entry? One is to create static tables in general. Not a good idea. It's not very scalable. Doesn't mean that they're static anyway, depending on the operating system. They might not be. And it's just not a very easy thing to do if you're in a large enterprise environment. So that's one way. It's not a great one, but if you have to, you have to. And in some instances, it may make sense in special cases to actually have static entries, but probably not in your entire network. What else can you do? I like to segment things. Once you segment things, ARP goes away as a problem because it operates at layer 2. And layer 2 only operates between two physically or logically, if you're in the wireless world, connected devices. So once I throw a router in the way, your ARP dies at the router. So what I often suggest to people is that they move servers and devices that are logged into to a different segment than regular users are on. I mean, it would be great to hope that every box on your network is locked down, airtight, but they may not be. If they have users on them, you may not be able to control how locked down they are. However, the server should never have users on it to where it could, Trojan itself or that kind of thing. Main issue with this is cost. Routers are expensive. In many environments, this would require a significant renumbering effort. And it adds complexity. Now you have to really understand how routing works. You can't just have one big static route, default 0.0.0 and everything works. You have to really get into protocols and understand how they work. So it's a viable solution, but it may not be the best one. The third way is really not preventing the attacks, but knowing that they go on. I think in the ARP world, that's probably about the best you're going to be able to do. So what are we trying to find when we do this? We're looking at packet anomalies. Like Jeff had talked about earlier, when the Ethernet and ARP fields do not match. They should always match. The problem is, the program that's actually detecting whether or not a duplicate IP exists, maybe it's getting its information from Ethernet and not ARP. So if you, excuse me, if those fields do not match, that's a good indication that something bad is happening. What else can we look for? We can look for reply and request matches. Generally, the problem that this attempts to solve is the updating of the cache with a request. Because, or actually, I'm sorry, the updating with a reply that does not have a request. You shouldn't see this on your network. If you do, it's a good indication that bad things are happening. Another third way, which is a little bit more difficult, is sort of like a statistical analysis of what MACs are ARPing on your network, how much, and to whom. So and of course we're open to other ideas. I want Jeff also to talk about the changes that have been incorporated into Snort to allow these detections to take place. We don't want to just talk about stuff, we want it to work.
So a couple days ago, Snort 1.8 came out, and some of this is actually in there. There's a new plugin that allows you to do a couple things. First, when we were doing this research, we found that a lot of hosts do some really weird stuff, like Linux boxes. As soon as you have an entry in your ARP cache, it periodically sends an ARP request to the host's hardware address that it already has in its own cache. It already knows its hardware address, but it persists and keeps asking, who's at this IP? But it already sent that person's hardware address a request, so it already knows. Anyway, it's really odd. It's a directed ARP request, and that's actually what we did for some of these attacks. But so there's an option that you can turn on in this preprocessor that says, I watch for directed ARP requests. Are they malicious? Possibly, but that's the opportunity to false positive. But so there's some other ones here. The mismatch between the ARP frame and, the ARP packet and the Ethernet frame itself. On an ARP request, if you have different information from the sender and the sender in the ARP frame, on a request, it flags that as a mismatch. And on a reply, it flags both the sender and the destination. Okay, so there we have a few of these. But the real big one is you can supply a list of IP addresses and MAC addresses in your configuration file, and when it sees a request or a reply come in, it looks at the sender IP address, and it matches it up to this list of entries you gave it. And if it's one that it has an entry for, it's going to take a look at the MAC address of the ARP packet it saw, either in the Ethernet frame or the ARP frame, as soon as the patch is out, and if it has different information in the packet it just saw from what it's in its table, it's going to alert on that too, because that's pretty bad. If you just told your IDS, this is the MAC address for this IP, and you see something else, well, that's pretty bad. So that's already out there, and there'll be some patches to that too.
So hopefully all the interesting ARP things that you learned today will not be of any value to you. Moral of the story, protect the data at other layers, or even a little more novel, I think, let the data protect itself. Questions, comments, complaints? No? Right on. Thanks. Oh,